I thought I'd begin by just saying a little bit about my interest in this topic and the work that we're doing. Most of this work is being done in a project called the Transformation of the Top and Tail. And that name probably gives you some clue, maybe a bit obliquely, as to what it's about. The thesis was that the smart grid technologies are going to play across the whole of the electricity distribution and transmission systems. But if we look at those bits of smart grid that are not so much control algorithms, but hardware technologies and infrastructure technologies, our thesis was that they play their role at the two extremes of the system. On the one hand, voltage source HVDC conversion is going to make big changes to the way we do national scale and international interconnection. And at the other end of the system, there's tremendous pressure on the local distribution networks, and there, again, power electronics and related technologies can have a big impact. So some of this work comes from the Top and Tail Transformation Project, and that's a 6-university collaboration and an affiliation with the Power Electronics Centre. And we at Imperial also have an involvement in 2 of the low carbon network fund projects that are relevant to this area. One called Low Carbon London, which has given us some insights perhaps into the use cases for power electronics in low voltage, and one that's just beginning called Flexible Urban Networks, where we'll get on to do some trials of some power electronics. So I'm going to draw a bit on those and reflect on those. I think the use of power electronics in low voltage distribution networks is interesting because it's one of the few remaining examples where there's still a debate on quite what the role of power electronics should be and whether the business case is quite there yet. I think in most other places where we attempt to apply power electronics, nobody's arguing that power electronics might not be the right way to tackle the problem. That debate was had some time ago and was resolved conclusively. I think it's interesting that it's not quite there in distribution networks yet. So I thought I'd start with a couple of pictures to illustrate that. And if we go to the top end, or the starting point of the electricity supply industry and generation, we know that if we want to operate wind turbines in an aerodynamically efficient manner, then we have to make their rotational speed match the wind speed. And to do that, we're going to have variable speed generators, and then we're going to use some power electronics to do some frequency matching. That was a picture of a power converter for a wind turbine application. It doesn't any longer really go in the nacelle of the wind turbine. It's going to go down here at the base of the tower somewhere. And that's a good example of where you'd probably have to go back 25 years to find the point where the debate was, do you resolve these issues about the aerodynamic efficiency of the turbine through mechanical and aerodynamic means, or do you shift that problem into the electrical domain and solve it with a variable speed interface to the generator? And that's resolved, I think. It's much more conclusive, perhaps even than that, in photovoltaic systems. The DC source needs to be inverted to make a connection to the AC electricity system. I thought this picture of a photovoltaic installation was intriguing because they've made a feature of the inverters, and I wonder where else people are making a feature of the power electronics as an architectural statement. If we go from generation to the national, international scale transmission systems, HVDC converter stations, an established technology over several decades. No one's arguing there's an alternative to power electronics there. The business case for going DC for submarine cables in particular is compelling, but also in terms of providing the reactive power needs of a transmission system. Using static power converters, STATCOMs, to do that is a well-made case, and it's cost-effective. And I don't think for this audience I need to spend any time at all really arguing that power electronics for conditioning and converting power in end use is compelling. Where it's a bit harder to find the illustrations for power electronics is in the distribution system. So once you've got the power to the bulk supply points for our cities and towns, then how do you distribute the power within that? You can find some nice pictures of, this is called a D-STATCOM, so a distribution level STATCOM, providing reactive power. Here's one I quite like that was built into containers and is relocatable. But not particularly widespread use, and we might come back as to why STATCOMs are not that widely deployed in distribution systems. Sorry, the feature of this photograph is mostly that nice sign saying SSE, but the interesting bit are the containers behind, which is a battery installation on Orkney. SSE are also involved in this project in the Thames Valley area with smaller scale batteries, what we call street level batteries. So the use there's much debate over the future role of storage within electricity networks to cope with intermittent generation. But the use case for home power electronics there is compelling. The point really is that the storage elements are still being trialled. Perhaps one place where it is well established is in static transfer switches, and that's this bottom picture here, where you want to do very rapid changeover between supplies on a critical load, then a semiconductor means to do that is compelling. But mostly, if you look at how distribution networks are controlled, it's very traditional equipment. This is a transformer, as you probably recognize, and that can on the left-hand side with all the connections going into it is the tap changer. So these are mechanical devices or perhaps now vacuum breaker devices, but a simple switching element. Much of the control out of the network are these things, teleoperated open close points to reconfigure the network. Still mostly done at the sort of tens of kV, in the UK practice 11 kV and 33 kV. An innovation in this area is about doing this teleoperated switch in small blocks that can fit into low voltage distribution boards, bringing that automation to low voltage, either in fuse boards in substations or in link boxes and whatever in the pavement. This is where power electronics has not yet made an impact, where it seems to me that whereas maybe 3 or 4 years ago I would argue that the business case is not yet made and their interest isn't there. There seems now to be the interest, and the demonstration projects are happening, is can we make enough innovation to make those demonstration projects effective? So I think I put this slide in mostly so that if you look back at the slide set, you've got some words around those pictures. That's essentially what I just said. And I should apologize, I didn't get my slides in time for them to go in the USB in the lanyard, but they will be up on the website. So if at the moment the distribution network is running pretty well with traditional means of electromechanical control, why are we talking about using power electronics in that arena at all? And it's really because of the things we think are happening or going to happen in generation and demand. So the first illustration, very clear, rooftop PV, a real big push from the feed-in tariff in this country, had already got well underway in many other European countries. And in several of those countries, beginning to see now the first signs that voltage control is becoming problematic in distribution because of the injections of power from PV at times when demand is low. The other thing, or the other two things, there's only one picture, is what's happening on the demand. Once, the policy is decarbonize the electricity sector, and then once you've done that, fold in building, heating, and transport into the electricity sector as an effective way of decarbonizing those two sectors. So the use of electric vehicles is going to put a significant extra load on distribution systems, and heat pumps for building heating, something also. So we threaten now excessive current flows in the lines and in the transformers because of the extra demand and to some extent generation when demand is low. Voltage drop and voltage rise problems, a change in the load cycling and the peak to average ratios of the loading of cables and transformers, and possibly power quality problems in distribution. Just as a quick example, and just as an illustration rather than a comprehensive one, this is a picture of some low voltage cables, 400 volt, 230 volt cables up and down a network of houses. You can see the street pattern. And we've been doing some studies looking at what happens when you deploy heat pumps on these, what happens to the voltages at the far ends of the feeders, and that's what that graph down here is. 50 houses on one of the particular feeders, and we put heat pumps on them in random allocations, and then plotting the magnitudes of the three phase voltages, and you see one of the phase voltages here dropping beneath the lower limit for a 230 volt network surprisingly early, after only 10 houses on the feeder were equipped with heat pumps. There's two reasons for that really. One is the UK practice of supplying single phase into houses, and the fact that often the houses are not evenly distributed between the phases, and if you complicated that by accidentally, as it were, or randomly putting heat pumps on that feeder, you can quite quickly find penetrations here. So this is a 20% penetration of heat pumps down that street. you're starting to threaten the lower voltage limit of the system. So network operators first approach, looking at how you do resolve these issues is traditional network reinforcement. So this is reinforcing a street just off Fleet Street, which I happened to walk down just recently, where building development, new office blocks or taller office blocks, causing a growth in demand in a very heavily or very dense demand center anyway, causing reinforcements. They're laying new 11 kV feeders up and down the streets to cope with that, and each time a new office block goes up, a new distribution substation into the basement to feed the additional load. In some areas, that's just getting very tricky to do. Finding land area to put new substations in or getting permissions to put new feeders down roads is problematic and time-consuming. Existing substations, this is an outdoor one in a rural area, this is an indoor one. Very little room in them for re-equipping, for taking the transformers out and putting larger transformers in or putting additional equipment in. And there's some opportunities perhaps to put new street furniture in, cabinets down the streets. So if we're not doing traditional reinforcement, what might we be doing? This is our opportunity for power electronics, clearly. We're going to try to avoid the disruptiveness and the expense and the time horizons over which traditional reinforcement happens by seeking to do things like trying to prevent the voltage limits getting in before the thermal limits. On many, certainly suburban feeder systems, the voltages start to hit the lower limit or the upper limit long before you hit the thermal limit of the current carrying capacity of the feeder. It's to do with the load density on those feeders. And doing better voltage control is something we could potentially be doing with the power electronics. As I already illustrated, often one of the phases limits before the other two, and that ought to be something that we can tackle with some phase rebalancing systems. We also have problems with certain feeders limiting before others, so we've got plenty of capacity maybe in the transformer, but not out on the feeders because one feeder limits first. Can we do some feeder-to-feeder balancing? And perhaps between transformers in adjacent areas, we'll touch on this a little bit later in the presentation, where transformers in different substations are used on different load cycles. And we may be able to alleviate power quality problems other than voltage level, perhaps addressing some of the harmonic issues that we're going to see. So can we make power electronics solve these sorts of problems, and can we make a business case for doing it over and above the case for traditional reinforcement? So that, of course, is a benefit to cost ratio calculation, which network operators are very well used to doing. The benefits we touched on, it's about utilizing existing network assets better to service a growth in demand or indeed in distributed generation, and defer and avoid reinforcements costs, and perhaps do something about network losses. If we can rebalance, get a more even current flow in the networks, perhaps we can reduce network losses to some extent. Johan this morning said that in many applications, if you talk to the industrial user of our equipment, the three top priorities are cost, cost, and cost. And I'm certainly not going to argue with that. If you go to a network operator, the question is, what's it going to cost for me to have this piece of equipment? Which you have to interpret as not what does it cost to buy, but what's the cost of ownership of the whole system. And maybe I'm pointing out the obvious, but let me do it anyway. It's capital cost, clearly, but in some of these applications, particularly in dense urban environments, it's the cost of land purchase and negotiation for land purchase. If we can avoid that, we're winning. It's the cost of losses over the lifetime, even at only 2 or 3% losses, amortized over the 20, 30-year lifetime of the equipment. The losses are a significant cost, and we have to tackle those. Cost of outages, unplanned outages due to equipment failure, come back as a real cost to network operators. And if we're going to try to improve reliability by a more strict maintenance regime, then we clearly have a cost of maintenance as well. And a couple of factors down the bottom here that I think are particularly important. Lifetime is an issue in cost because it's about replacement costs. And network assets at the moment have very long lifetimes, 30, 40, 50 years. Power electronics are probably on much shorter replacement cycles than that, and that affects your view of capital cost. And there may be additional costs when you put power electronic equipment in if you have to review protection and control systems and such. So, assuming that's what we've got to target, not just addressing the benefits, but keeping an eye on what we're doing about the costs as well. Looking at what the opportunities are, we'll start by just pointing out some differences between transmission networks and distribution networks. First of all, the X to R ratio is much lower. So that's the ratio of the inductive reactance of the cables to the resistance. We've brought the conductors closer together as the voltages have got lower, because the insulation requirement is down, and that means the inductive reactance is down. And that changes our view of that equation, the equation for a voltage drop along the line. Our colleagues in transmission networks just concentrate on the reactive power term because the reactance is big and the resistance is small. But as we go down in voltage levels, these two become either comparable or dominated by the resistive term. And that changes the way we do things. It means we put less reliance on the use of reactive power to control voltage, and we've probably got fewer ways we can intervene with reactive power anyway. And that comes back to what I said earlier about perhaps distribution StatComs, reactive power devices exist. We haven't seen widespread deployment of them because our problem is as much that as it is that. And the radial structure of the network suits the use of tap change transformers. All of our feeders tracking, or a feeder tracking back to one substation where we can make an intervention with a tap change transformer to change the voltage. But tap change transformers have their problems. First, in UK practice, we only fit them at this level, 33K to 11 kV, so we don't use them down the next level at 11 kV to 400 volts, which is where a lot of our problems begin to emerge. And you suffer the problem that all of the feeders on that substation go up or down in voltage together as you change the tap. And if you have one feeder where across the length of the feeder the voltage is falling because of a heavy use of EVs or heat pumps, but you have another feeder with a lot of photovoltaic injection, one feeder up and one feeder down, there's nothing you can do to move this left-hand point up and down with a tap changer that can solve both of those problems together. So it pushes us towards using stuff at the far ends of the feeders where you see the biggest voltage variation, where normally, this poor choice of word, practice is to have an open point, a switch one could close to provide an alternative route to supply a feeder if there's a fault further up the feeder. So that point normally runs open, but we have the two ends of the two feeders available to us, and we can do something with some power electronics, which is what we've come to call the soft open point. This is an open point, and this makes it soft by allowing some power transfer. Well, if I put back-to-back converters there, I get power transfer between the feeders, and I can pull a bit of feeder off the pull a bit of power off the generation-rich feeder and push it onto the load-rich feeder and even up the feeder use and bring the voltages back into alignment. I could attempt to do that with StatComs independently on the two feeders. I could do it in a multi-terminal arrangement. I could do it with a series-connected converter, which might be quite nice if that can be a partially rated converter, or a series shunt, sort of UPFC, Unified Power Flow Controller arrangement. So we've done a bit of work looking at that, trying to quantize the benefits. So this was a study of around about 611 kV feeders across southeast England, grouping them into substation groups of 6 or 8 feeders, and then placing power converters in several formats as StatComs or back-to-back converters, and at different ratings, and looking what it did in terms of saving on line upgrades. This is kiloamp kilometers of saved reinforcement. Somewhat busy slide that I pulled from a paper, but the point was that actually at 11 kV, and that's where this study was, you can do quite a lot with a StatCom, but the other converters are more effective. Series converter is a bit more effective, but the series converter is also really only a reactive power device, so it struggles. The UPFC, which can do real and reactive manipulation, is effective. It only processes a fraction of the transfer power, which is nice, and therefore it generally beats the back-to-back converter. But there are problems here. The back-to-back converters are attractive because they can shift power between two feeders, but shut down in the event of a fault and block fault current. So they operate to close the feeders for normal operation, but look like they're open under fault conditions, which means the protection system doesn't have to be redesigned. The UPFC, because it's partially rated, can't block the fault current. So although this might look a bit better, it might not be the one that flies. So having said a bit about 11 kV, I need to go down to where I was meant to be talking about low voltage feeders. The final mile is what we sometimes refer to it as. So low voltage here meaning 400 volts, three-phase, 230 volts, single. It actually represents probably about half the sunk cost of the network. That cost was sunk, though, probably 50 or 60 years ago. But it would be highly disruptive to replace that infrastructure. And much of it still has lifetime left. Here, the X to R ratio is less than 1, so reactive power is doing very little for us in terms of voltage control, so we have to do real power manipulation. It's here that unbalance between the phases is at its greatest because we have the least aggregation of loads, so high probability that one phase is going to be problematic before the others. And because substations feed groups often of quite similar consumers, adjacent substations have different use patterns, and that's an opportunity. Some might follow a domestic use pattern with heavy demand in the early evening, relatively light in the midday section, whereas a commercial district, maybe next door, has heavy use in the middle of the day, unless it's incentivized with tariff structures to do some early hours of the morning consumption. So here were some thoughts just about what one might do on low voltage feeders. So top diagram is just the reference point. It's a heavily loaded feeder with a substation up here which has no tap changer. So the first point maybe is if this point is low or high on volts, to put a soft open point, a back-to-back converter to a feeder on another substation. It relieves the feeder loading and could do that phase by phase, which is attractive. An often proposed solution is to actually replace the transformer with a fully electronic solution. So here, back-to-back converter arrangement, basically, but feeding the feeder so we can control the voltage at this point in a continuous fashion, unlike a tap changer, and perhaps have different feeders controlled differently, which would be attractive. Or if the problem is only one feeder, perhaps we just need to put a much smaller rated converter on one feeder. But often if the problem is about voltage, its far end of the feeder is the problem. So maybe we can further reduce the power rating of this device by putting it mid-feeder. This end of the feeder is largely okay. It's this end that is going to rise or fall, so do some voltage injection or voltage manipulation partway down the feeder. And perhaps the next step of that line of thinking is, well, why don't we just address the customers who have a problem and put point of load regulation in? Put power converters on the entrance to a house or a group of houses where there's a problem. So this is quite a lot of power electronics being deployed, but with the prospect of not having to rip the road up and replace that cable and build a bigger substation here. Because once you've done this point of load regulation, you then get to think, well, actually, maybe there are cuter things to do. First of all, if I put point of load regulation on all of the consumers, I could raise the voltage on the feeder overall and ship more power. And I could even turn it DC, so split my power electronics, so do AC to DC here, run a DC feeder, and then DC to AC converters at each consumer point. So a couple of words about each. The electronic transformer is probably the bit of this story that has received the most academic attention. It strikes me as one of those areas, I hesitate in this audience to name what I think the others are, one of those areas where there are more papers in existence than physical product, I suspect. But it's an interesting area to explore. The difficulty, or the advantages are closed loop voltage regulation at the output side, very attractive. Controlled fault current might be attractive, might be problematic. If we have traditional houses out here that have to blow fuses, the big 100 amp fuse at the entry to the house occasionally, then we've got to provide fusing current, and that's not something that power electronics is terribly good at. I've heard people argue that this arrangement could be small compared with traditional transformers. I think that is at the very least difficult to achieve. Perhaps one of its advantages is this high frequency transformer, and by no means is this the best or only way of doing this arrangement, could at least be oilless. and that might be an advantage in environmental terms to some of the network operators. But we clearly have problems. We've got to put all of the power through several conversion stages, so losses are going to be problematic. I think footprint is problematic, and cooling might well be. Interesting points, really, that in a lot of substations, the cooling is passive radiators. If we put fan blown cooling on these, we've got a potential audio noise problem. People are not used to that noise coming from substations, just a gentle hum. Okay, midfielder compensator I think is attractive. In this picture, it's a classic sort of series injection of voltage from some H bridges, well, these are bidirectional bridges because of the structure of the device. These only have to inject a relatively small voltage, so these are quite low rating, but they may have to inject voltage at a phase angle to the current where you've got to supply a bit of power or sink a bit of power, so you need a shunt connection to do that. But the shunt connection could be 4-wire, and this is the device that could do some useful work in terms of balancing current flows on the upper part of the feeder and indeed on that transformer. We could try to arrange a neutral current injection here that prevents or reduces neutral current flow in the transformer, which is a known problem. But if it goes mid-feeder, halfway down a street, it's got to fit in a bit of street furniture in a cabinet that's narrow enough to sit on the side of the pavement and not get in the way of parents pushing prams up and down the street. And we've got to hit the audio noise problem of putting power electronics in a location where it isn't expected. A lot of people got interested in turning the final mile DC. If the point is to not rip the pavements up and use the same infrastructure but use it differently, then we've got a couple of questions to answer. Sorry, I should have said, first of all, we've got an opportunity. If we do that, we can probably exploit the fact that most of those cables actually have 1,000-volt insulation, not 400-volt insulation. And we can go up to the 1,000 volts and stay at the 1,000 volts of DC rather than just hitting that as an AC peak. But some of those cables have been in the ground used on AC for 50 years, and we're now going to start using them for DC and then try to do an aging model to know when we have to replace them. And nobody really knows what's the aging model of a cable that's had decades on AC and is now used on DC. It is a big issue. If that's a 3-core cable with a combined neutral earth around the outside, then it's not obvious to me how you redeploy those conductors to make effective use on DC. And we have the problem well known in HVDC of how do you protect DC systems. So a lot of innovation, I think, and thinking needed if this solution is going to go somewhere. Okay. Spend a few moments, I might have to go through this fairly quickly, on a case study. We did it a little while ago to look at just in terms of losses and volume and such, is it tenable to do a back-to-back converter at these sorts of ratings? This was for an 11 kV pair of feeders. Wanted to move 12 MVA out of the converters, and we were postulating a 20 kV back-to-back link and meeting harmonic standards. So at those sort of ratings, you sort of fall between two camps in construction technology, I think. It's a bit like HVDC scaled down, and this is a picture from a HVDC converter station, but at medium voltage, only at plus or minus 30 kV. It's a voltage source converter for a wind farm just off Shanghai. It's, in fairness, probably a demonstration project rather than a product that is going to get rolled out. But you can see, even at 18 megawatt, this is a big valve hall. And actually, as Johan was saying this morning, you've got to watch how people are presenting power density. So this is the valve hall, this is the power electronics. There's another room the same size with the interface reactors in it, and there's another room somewhere else with the chillers for the water-cooled devices. So that's not the full view of the volume of this thing, and that's only 18 megawatt. This is, I think, if I lost track of the numbers for this particular picture, but I think about a 7 megawatt water-cooled machine drive in a series of 19-inch cabinets. So these are the two different construction techniques. This is clearly more compact. It's operating at lower voltages. But again, this doesn't include the chillers, and it doesn't include the sort of filters you'd need to meet the harmonic standards on a network application. But clearly people are doing stuff in container-type volumes at the sort of power levels we want. So we went a little bit further, looked at building these with a particular device. I think this device is now a bit old. We did the study a little while ago. It was a 1200 amp, 3.3 kV IGBT from Toshiba. It's got relatively high on-state voltage of 3 volts and is quite lossy in switching. That's why I say it's a bit old. We looked at a couple of different structures, the classic 2-level inverter, but with 12 devices in series in each, like a sort of first-generation HVDC converter. The multi-point clamped or diode clamped 5-level converter and a MMC-style 13-level converter. The first two use the same number of devices, 72. The MMC uses twice as many devices, but only 72 in the conduction path at a time. We compared them on filter use, so we've got to think about the AC side filter for harmonic purposes, and we've got to think about the DC side capacitance to support the voltages of the multi-level in particular. So we looked at a filter design and changed that filter as the quality of the waveforms changed. And what we saw was for 2-level PWM at about 2 kilohertz, I think it was, we needed a 10 millihenry inductor here, but that could shrink by a factor of 10, at least in inductance, and probably therefore in volume, by going to multi-level, or a high number of levels. But interesting, though, on big-scale MMC, you can dispense with the filter. At these sorts of level numbers, you still need a filter of some sort. So the MMC wins, except when you look on the DC side, you need capacitors to maintain all of the level voltages. So quite a large capacitance bank of 36 4 millifarad capacitors, big ones at 1.7 kV, giving a big total volume. The 2-level converter doesn't entirely escape having a big DC link capacitor if you want to support zero sequence or negative sequence current flows, unbalanced current flows. You then need quite large capacitors. There's a bit of a trade-off between whether your passives are on this side of the converter or that side of the converter, and an optimization job to do, I think. In terms of losses, and this is probably where the numbers would get better if we redid the study, going from almost 3% losses in the 2-level converter, because you have to double this for a back-to-back arrangement, down to just over 1% for the MMC version, which is about where we might want to be. But one of the things we found was that the no-load losses are quite significant. You try to run with zero power transfer, but you're still supporting the currents in the filters, and that gives rise to quite considerable losses, even when notionally running at no power transfer. So on that, we find the volumes overall quite challenging for use in a substation environment, shipping container-sized power converters. Not a lot of space to fit those in existing power stations, substations. Probably the MMC wins overall, although big DC link or DC side capacitor use. Back-to-back format, we could probably on that study achieve 97 and a bit % efficiency, and we could probably improve on that. But I think there's some way to go before power electronics of these sorts of power levels and tens of kV are going to come in with the efficiency and the size that we require of them. And a final point, that was assuming we could get away with water cooling, and there's no history of using water cooling in substations. Okay. Having said a bit about the hardware side of the power electronics, I think it's worth spending a few moments thinking about network compatibility from a control and system modeling point of view. Again, I think Johan set this up for me a bit. There is a community of power systems engineers who don't really understand what we as power electronics people talk about. And we as power electronics people don't often understand what it is that really drives the decisions and the concerns of some of the power systems people. And some of the examples are in here. Key thing for a power system planner to do is to do a protection study. How much fault current appears at various breaker and relay locations around the network when you throw various sorts of three-phase and single-phase faults, etc. Once they do a protection discrimination study, make sure that the right breaker's open, and so it needs a fault current model. They need a transient model, so when there's large signal disturbances or we know the system is stable. Does it recover in a stable fashion from a fault? Is it prone to small signal stability issues? Are there control loop interactions or interactions between the dynamics of different pieces of equipment that give rise to problems? And wants to do power quality studies, which is often a harmonic load flow. So wants to know harmonic impedances of the network and of the devices. And perhaps that extends into dealing with negative sequence or unbalanced conditions. So that's where I think as power electronics engineers, we have a duty to try to present what we do in a way that a power systems engineer can grapple with. So we might look at an inverter in a fault current and think, well, what I need to do then is model my converter, the physical bit and the control loops, and then put that in a simulation and throw various faults and look at what happens. So that's quite a complicated system. I mean, we can cope with it, but it's reasonably complicated. But now if you have a feeder of 50 houses and you do that on several substations and you run what would need to be a time domain simulation to find the fault currents, it becomes tedious and is just nothing like what a power systems engineer does, which is say that generators behave as voltage sources behind an impedance, and then you calculate the fault currents. So we need to reduce all of that stuff down to something that looks like an equivalent circuit that can go into a fault study. We've done a bit of work on that. I'll just show a slide. So we've found ways to reduce the inverter to an equivalent circuit for different classes of faults, and then gone to try to verify those in the lab. So that was the lab setup with a cluster of 3 inverters on a feeder and a 4th inverter showing, emulating the grid, and then throw various faults. This was a phase-to-phase fault, so an asymmetric fault. And you see that in the time domain waveforms here close to the fault. 2 phase voltages are pulled together and the 3rd phase voltage pushes up, and you get a series of fault currents. And the solid lines are what are predicted by the impedance, equivalent impedance model, and that agrees quite well with the time domain models. Something similar, I think, on transient stability or fault ride-through. It's, do the converters come out of fault limiting in a sensible fashion, in a sensible time scale? And I think this is complicated because there are just so many ways of implementing current loops and current limiters and voltage limiters in converters. And it's hard for a network operator to be assured that the devices will come through a fault and be available again to supply power or to supply control services post-fault. And if they're no good, if they're not available post-fault, then there's a serious problem, clearly. So quite a large piece of work, I think, to present the information back to the power systems community in a digestible format. One of the things I didn't touch on earlier, or not very much, in terms of what the motivation is, there is a case to try to tackle harmonic distortion and power quality. Until recently, I was fairly skeptical of this case. I have to say, I thought, well, provided all our devices are IEC 61000 compliant in terms of harmonic emissions, then we ought to have a fairly clean set of currents on the network, and therefore a fairly clean set of voltages, at least going forward. I think the heat pump study in particular taught me that if you have a collection of heat pumps that only just comply with IEC 61000 and you accumulate them on the feeder, then you're quite quickly into voltage limits particularly on the low order harmonics. So I think there is a case for doing some harmonic mitigation, and I quite like the idea of doing it through emulating resistors at the harmonic frequencies. And this is a set of control loops one can add to an inverter to measure the harmonic voltage, synthesize a reference current for that harmonic based on an assumed impedance, and add that into the current controllers. And I quite like that because it's a way of adding a sink of harmonic currents in a way that adds damping to the network. And it's also a way which is understood by power systems engineers. Now they have an additional set of harmonic impedances, which are harmonic resistances, to add to a harmonic load flow. Oh, sorry, I'd forgotten that I had a little illustration. That's a distorted set of voltage waveforms. This is the control loop cranking up the gain of the resistive compensator, and gradually you draw more and more harmonic current into the device, and that cleans up the voltage waveform. And if the locally distorting load goes away, then the current reduces almost immediately because the harmonic voltage driving it has gone away. Quick sort of penultimate slide, I think. Just quick few words about control. Distribution networks have very little infrastructure for monitoring and communication at the moment, and there seems still to be a resistance to rolling out, measure everything and make it available. We are going to have to live in an environment for some time where communication back to the central control room is on 10-minute intervals and is for monitoring and for optimizing the network configuration, not for closed-loop control. So the services to the network have to be on the basis of local control loops using mostly local measurements and perhaps some dedicated remote measurements. So decentralized control methods based around droop settings and impedance presentations, I think, look attractive. There is, of course, a lot of talk about using agent-based software to do control in distribution networks as part of the smart grid paradigm. But that's still assuming really quite widespread availability of communication between agents. And I think that's still looking problematic. And to wrap up, almost on time, I hope. I think the use case for power electronics within distribution systems has become much clearer in recent years. That's not to say that power electronics has bought its way onto the system yet, but we know how it's going to do it, I think. And it's a lot to do with easing voltage constraints on the assumption that loading on the networks is going to get much heavier in future. And to some extent, it's about intervening to balance up line flows as well. I think, although I didn't spend a lot of time discussing this, the converter topologies that don't process all of the line power, process a fraction of it, are attractive. And if you can process a fraction of the power for a fraction of the time, then your problems around footprint and efficiency all ease. Network compatibility, I think, is important. It's crucial. We've got to present these solutions to network operators in a way that they understand, particularly in terms of the treatment of, or the management of faults, the treatment of unbalance, and the treatment of harmonics. And it's all about the whole life, whole system costs. My final point is about there are research opportunities there and challenges to address, but essentially we've got to make sure we're addressing the right ones. And my sense is the emphasis is more about, are we bearing down on cost and volume and all of those good things and losses, rather than are we creating new control functionalities for problems that may or may not be relevant to network operators. It is about really focusing the attention on the things that we can do that reduce the impediments to deployments of these technologies. I think we have to acknowledge it is hard for university researchers, at least, to be able to work accurately on the basis of costs, but we know the factors that influence cost, and we should be able to work on those factors. Okay, that's what I had to say. Thank you very much.